Welcome to another lesson on the OpenFoam guide course. I hope you are doing great. In today's discussion, we see a crucial aspect of computational fluid dynamics, initial and boundary conditions. This topic is so important that we will cover it in two videos. In the first video, I will explain initial conditions, how they define the starting state of your simulation. In the second video, we will focus entirely on boundary conditions, which dedicate how your system interacts with its surroundings. Whether you are simulating airflow over an aircraft, water flow in a pipe, or combustion in an engine, the initial and boundary conditions you set can make or break your simulation. Let's break down why they matter and how they are implemented in OpenFoam. So in this first part, we will review what initial conditions are and why they matter. See how to implement uniform and non-uniform initial conditions in OpenFoam. And at the end of the video, I will share some professional tips with you while you are setting your initial conditions. So what is initial conditions? Initial conditions is the state of the system at an initial time. It serves as the baseline from which the transient behavior of the system is computed. To explain this, let's see this exponential decay initial value problem. Say we have this differential equation describing exponential decay. The general solution is like this one here. But to find the constant c, we need an initial condition. Say y at time 0 is equal to y0. Substituting this, we get the final solution like this one here. And it's clear that the solution depends entirely on the initial state y0. Let's visualize this with a Python script. So here you see how different initial conditions lead to entirely different curves. This is a universal concept in CFD actually. In CFD, your results are sensitive to your starting point, especially in turbulence flow. And for more dramatic example, we consider the Lorentz system, a classic model for chaotic behavior. So in Lorentz system, any tiny changes in initial conditions lead to widely divergent outcomes. It's a phenomenon known as butterfly effect. Now let's move to practical implementation. We will solve the heat equation in OpenFoam to demonstrate uniform and non-uniform initial conditions. Here is the heat diffusion equation, where U is the temperature at a specific position x and time t, and alpha is the thermal diffusivity constant. And to solve this transient problem, you will need initial and boundary conditions. The first problem is 1D heat conduction in a wall. The second one is 2D heat diffusion in a plate with a hot spot at the center. We start with the classic example, heat transfer by conduction in a solid wall. For simplicity, we will model this as a 1D problem, and for initial conditions, we set the temperature to be 27 Celsius degree everywhere on the domain except the boundaries. For boundaries, we have a fixed temperature value at the left and zero heat flux at the right. The goal of this simulation is to determine the transient temperature profile across the wall as heat diffuses from the hot left side to the insulated right side. Let's navigate to our first problem's case directory. As we know from previous videos that every simulation in OpenFoam follows a standard directory structure that organizes all the necessary components and the libraries that needed for the simulation. Here is what we have. The 0 directory. This contains the initial and the boundary conditions file for all field variables. In our case, we had the temperature field file, T. The constant directory. This holds two components. Polymesh, which contains the mesh data, which we haven't generated yet. Material properties. For this simulation, we will define thermal diffusivity here. And the last one is the system directory. This is where we control the simulation's execution through three key files. Control dict, which sets time controls, solver selection and output intervals, and so on. FEV schemes, which defines numerical schemes for discretization. FEV solution, which configures solver algorithms and tolerance. At this point, I could jump straight into the T file to show you how to set initial conditions. However, I want to take a more comprehensive approach by walking through the complete CFD analysis workflow. This way, you will not only learn about initial conditions, but also understand how they fit into the bigger picture of a simulation. So first things first, we are going to determine the domain where the heat equation will be solved, and then generate the computational mesh. Actually, these two steps can be done using BlockMesh tool, as BlockMesh allows us to create the domain and generate its computational mesh. First, we define the vertices that bound each block. In this simple geometry, we use only one block. Then we define the block and the grid settings. The last thing to specify here is the boundary name and type. We set the left and the right faces to be batch type and the other four faces to be empty, as we want to solve the heat equation in the x direction only. Now we execute the command inside the case directory to generate the computational mesh. With our mesh ready, we will now define our material properties. In the constant directory, we open the file and add the thermal diffusivity value. Say 10 to the power of minus 4. With our geometry and the material properties configured, we are ready now to move on to the most critical part for this lesson, setting up our initial conditions. This is where we will define how our system starts before the heat diffusion begins. The initial conditions for each field like velocity, pressure, or temperature, as in this case, have their own input file. And the file is named exactly after the field it represents, under one directory whose name reflects the time layer. Now let's examine the temperature field file in detail. The first section here is the header of the file. Then it's followed by three main entries: dimensions, internal field, and boundary field. In dimensions, we define the unit of the field via the list here. OpenFoam uses a precise system for handling units through dimensional analysis, as this list contains the exponent of the SI base units, which are 7 units. It may be a challenge here to remember the order of the SI base units specified in the list to adjust their exponents to reflect the desired unit. For example, for temperature, the SI unit is Kelvin, so I need their exponent for all units except for Kelvin to be 1, positive 1 to be specific, which is the third index here. Remember, we count from 0 index. So you need to remember this order. Or you can check the source code as a reference for the dimension set by opening dimension set.h file. From this file, you can know the quantity, SI unit, and its exponent order in the list. First quantity here is mass, and its SI unit is kilogram, and so on. So back to our field unit, we need Kelvin. So the base unit will be kilogram to the power of 0, meter to the power of 0, second to the power of 0, and Kelvin to the power of positive 1, and so on for the rest of the 7 units, which eventually equals Kelvin. Let's see how to represent meter per second in this list. It will be something like this. Okay, back to Kelvin again. Okay, next entry is internal field. where we finally define the initial conditions for our field. In this simulation, we are using a uniform initial conditions. A single value is assigned to all internal cells. To specify this, we write the internal field keyword followed by the type of the field, in this case uniform, and then we write the actual value. For example, to set a uniform temperature of 300 Kelvin, which is a scalar field, the syntax would be like this. However, if you are working with a vector field such as velocity, you will need to provide three components, one for each spatial direction, x, y, and z. Also, when using vector values, make sure that the class of the field is defined as vector field in the corresponding file header. The final entry in the file is the boundary field, where we define the boundary condition for each face of the domain. For each boundary, we specify both the type of the condition and its corresponding value if needed. We will go into more detail on boundary condition in the next video, but for now, let's do it quick. The left boundary is set to a fixed temperature value using the fixed value type. In this case, we assign it a value of 323 Kelvin. The right boundary is set to zero gradient, which means the gradient normal to the boundary is zero. This implies no flux across that face. All other faces are defined with the empty type. Now our problem is mathematically complete. We can also visualize it. So far, we have completed the post-processing for our simulation. We defined the computational domain, generated the mesh, specified the material property in the constant directory, and finally, we set the initial and boundary conditions. Now we are ready to move on and solve the heat equation. For this problem, we will use Laplacian foam, a specialized solver for scalar transport fields, like temperature in this case. For more details, you can visit the source file for the solver. The solver settings are in these three input files. In control deck, we specify from which time layer the simulation should start. In this case, it's from the zero layer, which is in the zero directory, but it can start from any other time layer if you have another layer to start from. You also adjust the parameters in these two files. And finally run the simulation. Here we go. Next, we visualize the results and plot the temperature profile across the wall to see how heat is conducted from the left boundary where we applied a fixed high temperature to the right insulated boundary. And that is all with a specific initial condition. Now we move on and see how we can apply a non-uniform initial condition. This will be in the second problem. In this simulation, we consider a 2D plate with insulated boundaries in all sides. At the initial state, the plate has a high temperature region located at the center, while the surrounding area are at a lower temperature. The goal of this analysis is to observe the heat diffusion over time, starting from this center hotspot and spreading outwards toward the edges of the plate. For instance, we can copy the wall case and adjust it to match this case. We are going to change the domain to be 100 by 100 millimeter. And add 100 cells in the Y direction. Then remove the top and bottom face from the empty type And as all boundaries except the front and the back will be insulated, so I group them together under one name and type. Okay, for thermal diffusivity, I will keep it. Now we open the T file and see how we are going to carry out the non-uniform initial condition. The dimensions will be the same. And for boundary conditions, we will apply zero gradient on all sides except for the front and the back patches, which will be set to empty. Okay, now for the non-uniform initial condition, it's a bit more complex than the uniform one. First, you change the type to be non-uniform, followed by a list keyword. Then you specify the type of the values in the list, scalar or vector. Temperature is a scalar one. Then followed by the number of the values in the list, which is equal to the number of the cells. Say a domain contains 200 cells, and finally you write the list of the values for each cell. In the end, your entry will look something like this one here. But let's be honest. Manually writing out a non-uniform field like this is not practical at all. Even if you write an external script to generate this list for you and paste it here, in complex geometries, it would be impossible because there is no straightforward way to keep track of cell indices across a large or complex domain, and any message changes will invalidate the entire list. So that OpenFoam offers a much smarter solution for this, a utility called setFields. This tool allows you to define different field values in specific regions of your domain. Alright, so how do we actually use the setFields utility? Well, here's a tip from my own workflow whenever I'm learning something new in OpenFoam, especially ones that aren't well documented. I look for a tutorial case that already uses the tool I'm trying to understand. Then I run it, explore the files, modify a few parameters, and rerun it again. This hands-on trial and error really helps build a solid understanding. And it's exactly what I'm gonna do now with setFields. So let's go to the tutorials and find a case that uses setFields. A good way to do this is by searching for the setFields text file. And I'm going to use the laminar dam break tutorial. It's already explained in the user guide, so you can follow along there if you want more details or background. Now to keep things focused, we are going to concentrate on just two things. The field that is being initialized, in this case, this is typically the phase fraction field alpha.water and the setField text file, which defines how this field is initialized across different regions of the domain. To better understand this problem, let's run blockmesh and open the case in PowerView. Here we are visualizing the field alpha.water at the beginning of the simulation. As you can see, the value is 0 everywhere, meaning there is no water in the domain initially. If you didn't know, here alpha.water refers to the volume fraction of water that is used in the volume of fluid method. So an alpha value of 1 means a cell is completely filled with water, while a value of 0 means there is no water in the cell at all. In this case, what we want is to start with a column of water on the left side of the domain, and then let it flow under the effect of gravity. To do this, we need to assign alpha.water to 1 to the cells inside that column, and alpha.water equals 0 elsewhere, which makes this a classic non-uniform initialization problem. We can apply this setup with a single command. Just run setFields inside the case directory. Now we refresh ParaView, and here we go. The water column appears as desired. But how does this magic actually work behind the scenes? Let's break it down by looking into the setFields text file. Let's delete the generated initial conditions and walk through the setup step by step. Initially, alpha.water is set with a uniform value of 0, which means there is no water in the domain. And that is not the setup we want for the simulation. Instead, we will use the setFields utility to generate the non-uniform field for us. And the instructions for this utility are written in the setFields text file. This file contains two main entries. First entry is the default value for the field. In this case, alpha.water is set to 0, which applies to the entire domain. Then we set a list of regions where we define areas that need a different value from the default one. Here we want alpha.water to be 1 at a specific location to represent the presence of water. So here we define this region. To define a region here, we will use a box shape, but you can use a sphere or I think a cylinder. So here you just need to define the body diagonal of the box. That is x1, x2, y1, y2, and z1, z2, just to specify the body diagonal of the box. Once we have defined the box and assigned the value alpha.water, we save the file and run setFields inside the case directory. You will see the output from the command in the terminal showing what has been done. Now refresh ParaView. There it is. The water column has been initialized. Let's do something different. Suppose we want to add another water column on the right side of the domain. We just add another box and run setFields again. And here we go. Finally, if you open the alpha.water file, you will see that the internal field is now a list of non-uniform scalar values between 0 and 1 corresponding to each cell in the domain, exactly as we intended. Let's simulate this for fun. Alright, let's get back to our main simulation. First, let's clean things up. And to save time, we will copy the setField direct file from the dam break tutorial into our current cases system directory. Before we make any changes to the file, let's visualize the domain and the current initial conditions in ParaView. And check skip 0 time to load the initial field. Front and back not found in object T. I think there is a spelling mistake in the boundary names. Let's check. And yes, there it is. A small typo, so let's correct that. Okay. We see now that temperature field T is set to 0 Kelvin across the entire domain at time 0, as expected with the current uniform initialization. What we want to do now is use setFields to define a non-uniform temperature field. We need 400 Kelvin at the center of the plate and 300 Kelvin everywhere else. Now we modify setFields direct to achieve this. Now let's go ahead and modify the setFields direct file to fit our case. First, we change the field name from alpha.water to T. Since we are now working with the temperature field, also update the default value to 300, which will be the background temperature across the entire domain. Then in the regions section, we also change the field name to T and set the region value to 400. Finally, adjust the geometry of the region itself. Let's define a box that covers the center area. Okay, now we save the file and run the setFields command. And now we have the initial condition set exactly as we intended. If you open the tfield file, you can see what setFields has done. So instead of having a single uniform value, it has written a non-uniform scalar list. Alright, let's go ahead and run the simulation. Rescale to data range, and here we go. Now that we have covered the basics of initial conditions, I think it's enough for this tutorial. However, there is one important concept I want to clarify, which is initial conditions in steady-state simulations. Take the Poisson flow we simulated in the previous videos as an example. While this is a steady-state simulation, we still defined initial conditions for the system. So you might be wondering, what exactly do we mean by initial conditions in this context? In steady-state simulations, the values of the internal field are considered as initial approximation for the iterative solution process. Essentially, these initial conditions are just starting guesses for the solver. Theoretically, it doesn't matter much what you choose for your initial approximation, the solver should converge to the same final solution. However, in practice, it's highly beneficial to initialize the domain with the values that are close to the expected solution. And that brings us to the end of this lesson. Before we finish, I would like to share some tips to help you perform more accurate CFD analysis. Let's take a look at a few key guidelines on how to choose effective initial conditions. Tip number 1. Use experimental data when available. Whenever possible, base your initial conditions on experimental results. For example, wind tunnel data can provide excellent baseline conditions for your aerodynamic simulation. Tip number 2. Start from a previous simulation. If you have already run a similar simulation, maybe with a coarser mesh, different solver settings, or different material properties, reuse those results as initial conditions for your new simulation. This is a common and effective strategy for saving computational time. For instance, you can even solve the problem first using a coarser mesh, then use those results as initial conditions for a finer mesh simulation. Or use a faster solver like OpenFoam to generate a rough solution, then switch to a more accurate solver for refinement. Tip number 3. Apply physics-based estimates. When experimental or simulation data isn't available, use theory to estimate reasonable initial values. For example, in laminar pipe flow, you can use a parabolic velocity profile as initial conditions. Tip number 4. Avoid unrealistic values. Initializing all variables to 0 isn't always a safe choice, unless it's physically applied. For instance, in high-speed external aerodynamics, starting with 0 velocity can lead to instability or longer convergence times. Instead of that, initialize the velocity field using the free steering velocity to give the solver a head start. Tip number 5. Test sensitivity. Finally, test how sensitive your solution is to initial conditions. And this is by running several cases with slightly different initial values. This helps ensure that your results are robust and not extremely dependent on a specific starting point. As you see, smarter choices in initial conditions can reduce computation time, improve conversions, and lead to more accurate solutions. So next time you set up a CFD case, think carefully about your initial conditions. Your results depend on it. Thanks for watching, and I will see you in the next lesson.